This video explains the journey of prompts in vLLM. We start with 3 example prompts. The tokenizer takes each prompt and converts it into word token ID pairs. As each prompt enters the tokenizer, it transforms into its tokenized representation. Model execution contains 2 phases. The prefilling stage, where the model processes all prompt tokens in parallel, and the decoding stage, where the model generates new tokens one step at a time. This is the prefilling phase. Each prompt embeddings moves into the transformer block, and their key/value pairs are calculated for every token. This occurs in every transformer layer, where each block computes the key value cache for each token embedding at every transformer block. In the following sections, we will explain how exactly these key values are stored. As shown, all input tokens have their key value caches computed in every layer. That's the reason prefilling is compute-bound. Let's take a look at the decoding phase. Each prompt shows its full key value pairs, including the newly added tokens from the prefilling phase. As shown, only new tokens do not have key values for this step. When these tokens are passed through the transformer layers, only the new tokens produce fresh key value entries. Previous KVs are reused from the cache. Because we compute KVs only for newly generated tokens, decoding is memory-bound rather than compute-bound. The scheduler prioritizes decode requests over prefill ones. Let's look at memory management. Suppose we have 40 gigabytes of memory. What resources need to be allocated when loading a model into it? The first allocation is for model's weights. In this example, it's 13 gigabytes. PyTorch temporarily uses memory for activations during computation, for example in prefilling, and this represents the peak of that usage. The remaining GPU memory is reserved for KV caches. We will deep dive into this section later. Some memory is also taken by system components like CUDA kernels and drivers outside of PyTorch. The KV cache is organized into blocks, which serve as the main units used by page attention. Block size is dynamically calculated based on each model specifications. Let's take a look at how each block is allocated. By default, each block has space to store the key value of 16 tokens for all layers. To calculate each block size, the model executor gives us 3 key pieces of information: the number of transformer layers, the number of attention heads in each layer, and the size of each attention head. Using these 3 pieces of information, each layer's space is computed from the number of heads and the head dimension. Since a block stores key value caches for 16 tokens across all layers, we multiply the per layer requirement by the total number of transformer layers. Each block must have enough space to hold key value data for every layer. To compute the memory footprint of each block, we multiply the number of transformer layers, 4, the number of tokens per block, 16, the 2 cache types, key and value, the number of heads, 2, the head dimension, 2, and the bytes per value, which is 2 bytes here. This results in a block size of 1026 bytes in the figure. Here you can see the actual block size when loading Llama 7B, which is approximately 8 megabytes. For simplicity, let's assume each block can store only 4 tokens. For example, if we have 3 tokens, we would use 75% of a block to store all key value data across all layers for those tokens. The actual blocks live in GPU memory, where they are referred to as paged KV cache memory. Depending on the GPU's VRAM and the model specifications, we can allocate up to hundreds of thousands of these blocks. On the CPU side, we maintain a queue of free blocks, and the KV cache manager always points to the first available one. This queue is implemented as a doubly linked list. Now let's return to our original example, where we have 3 prompts at time step 1. The scheduler determines how many prompts can be processed in this engine step. In this example, assume the GPU has enough space to handle all of them. The first block is assigned to the first 4 tokens of the first prompt. The second block is assigned to the last token of the first prompt. Each token has an offset that indicates its position within the block. Similarly, the KV cache manager assigns CPU block IDs for the remaining prompts, and the offset for each token is computed as well. Here we introduce slot mapping, a key concept in paged attention. It maps logical IDs to their corresponding physical IDs. For example, if the logical position is 8, its corresponding physical position is block 2, offset 0. To compute the logical address for each physical position, we multiply the token's block ID by the block size, and then add its offset within that block. This gives each token a unique logical slot. We demonstrate this process step by step for the first prompt. The same calculation is then applied to the second and third prompts to determine their corresponding logical addresses. Now let's reverse the process. Given a logical address, we find its physical location. For example, logical address 17 divided by the block size, 4, gives the block ID, and the remainder gives the offset within that block. All these tokens are then concatenated into a single continuous batch and sent to the model executor. After one step in the model executor, suppose it generates 3 new tokens, 1 for each prompt. As before, the slots for new tokens are calculated. Then they will be added to the continuous batch in their correct places. And their corresponding GPU blocks are updated accordingly. In the next time step, let's say again we have 3 new generated tokens. A new prompt also arrives at this moment. It is tokenized by the processor, assigned a request ID, packed as a request, and then placed in the waiting queue. To learn more about the core components of vLLM, watch our video explaining how it works. The last block of the first prompt still has space to fit the new token. Same as before slot mapping is done, and the token resides in its block. The last block of the second prompt is now full, so the KV cache manager allocates a new block for that prompt. The slot mapping is updated accordingly, and the new token is stored in the newly allocated block. The last block of the third prompt is also full, so a new block is allocated for it. The slot mapping is then updated based on this new block. Thanks to the improved design in vLLM v1, each step can handle both decoding and prefilling requests simultaneously. This means the new request is processed in the same step. The KV manager allocates the necessary blocks, computes the slot mappings, and places the request's tokens into the appropriate GPU blocks.